Hi there, we are back with a collection of educational papers. These ideas I think every AI researcher should know about. The first paper is about Shaef neural network. Using the concept of Shaef, we take a mathematical structure and we augment it and we make it better. We have some notions of local and global data and some notion of refinement. So you can think of it as like you have some data that have to be consistent with each other at different levels of abstraction. So the concept of Shaef, you can see the nature of local and global here. Let's see an example. Suppose that we have this graph. We have a set of edges and a set of nodes that are connected. We can associate to each vertex or an edge a stack. So a stack is something just like a vector space that we associate and augment the graph with that data. We can have like arbitrary stacks, but we require that these stacks play nicely together. So we have some restriction maps that has to be satisfied. Like a map between the node and edges play nicely together. So this is our notation and we call this like a sheaf of vector spaces on the graph. Here we take a part of the graph like two node and edge and we apply our construction like we associate each node a vector space and edge a vector space. Now that we have associated to each edge and to each vertex like a vector space, we can have a linear transformation between them. And we can take elements in this vector space. So an element from each stack of the sheaf is called a section. These sections, we can apply the linear transformations to them and get some vectors. And as you can see, these vectors may be different for the edge that we had above. Like we get a different vector if we apply differently linear transformation associated. So this stack, in order to be consistent and we get the same vector, they have to be in a global section. So you can see in the below that after applying the linear transformation to the vectors, we get the same vector like on the edge in the vector space associated to the edge. So we have like some consistency. Note the only structures that we needed to construct a sheaf was a partial order. We can have more complex sheaf structures. For example, on a topological space, we can have a sheaf of abelian groups on the space that assign to each open set an abelian group. So this is a more complex example of a sheaf. If you are interested, you can have a look at it. But the concept of sheaf on a graph is sufficient for understanding the Shaef neural network. So our paper, Shaef neural network, presents a generalization of convolution network by generalizing the diffusion operation on a graph neural network. So we have like the base structure, which is a sheaf, and the information propagation, which is done using the diffusion. And we use a concept of the sheaf Laplacian, like the graph Laplacian, which is a generalization, and we can define it for the sheaf. So a cellular sheaf is something that we already know. It is like a vector space associated to each vertex of a graph and edge, and we have some restriction maps that we said that they will play nicely. So the notation is the same here. We are just defining the vector spaces on the graph, and we have the notion of consistency like in the global section and etc. The concept of Laplacian and etc. are defined also here. So the main message here is that we take a mathematical structure and we can make it somehow trainable. And the author and the paper goes on by defining the sheaf diffusion operator and like how we can propagate the information on the sheaf neural network. And we already know that notion of the like H superscript 0 was the cohomology group, or we say our global section and etc. But here we also define a notion of sheaf convolution, which is just the matter of notation and combining the ideas that we already know. They use this in a semi-supervised classification task, which we have a data imputation problem. You can see also the results where it performs better, like in this task, and we have how it compares to the graph convolution networks. The next paper that we are going to have a look at is Simplicial neural network. Already in the homology and cohomology video, we defined the simplexes. The simplex is just a generalization of the graph neural network again. And they define a notion of convolution on these structures again. So it is like doing view the data as topological spaces in general, or simplicial complexes. So we define the simplexes to be like 0 simplex is the vertex, 1 simplex is the edge, 2 simplex is a triangle, and so on. We defined like boundary maps that like the boundary of the triangle was its 3 edge, and this is notion of the boundary map and etc. And we can present some data in these simplexes, like a co-authorship simplex. Like A, B, and C have paper together, so they form a triangle, and A and B are the edges, and they have a triangle. So we can define like Laplacian and etc. for these simplexes also. and we have a concept of Laplacian on the simplicial complex that can be defined using the boundary and co-boundary maps that we have. So the notion of convolution again is defined, and this is the same idea, but we have a different structure relative to the Shaef neural network. We are taking a simplicial neural network and we build add structures on that. So we define a simplicial convolution and etc. And again, we are using it for a data imputation task. Like we have missing data and some part of the network and it has to be inferred. So on our simplexes we have missing data and we are inferring the data using the new network that we have. And you can see the co-authorship complex, like how it is constructed and etc. You can study the paper for more details and have a overview of what we have discussed so far. In the series of next papers, we take the manifold and its structure and we somehow make it trainable. In this paper, Deep Riemannian Manifold Learning, we are taking the idea that we can have a trainable metric and we can infer like geodesic and distance on the manifold. So this is also very useful in some tasks. In the manifold video, we already discussed a little bit what a Riemannian manifold is. So I had the concept of the manifold and the metric and the concept of geodesic also, which was the second order differential equation. And this formula represents the geodesic, and we have like Christoffel symbols in the geodesic formula. In this paper, they try to present a manifold by a single chart. So we have just like a single chart. Our manifold is diffeomorphic like to the Rn. We construct a metric in a local coordinate as a symmetric positive definite matrix or an SPD matrix. So basically what we are doing, we have a neural network that has to learn the metric. And by just like we have two functions like this sim function and fn function. And using the exponential map, we can represent the metric as a learnable function. And they prove that this on a compact set of Rn or neural network can represent a metric. So we use this idea to embed graphs into a manifold. So this gets a little weird, like we have a curved surface and we are embedding a graph or nodes of the graph on the surface, but we have to preserve the distance. So you can think about it, how this has to be done. And this neural network is really something. You can study the appendix for a review of the manifold and etc. Next paper is about using differential forms. So like they use the differential forms to create a representation of simplexes. In this paper, we are trying to represent the differential forms or a K-form as a neural network. So a multi-layer neural network represents our differential forms. And this is again taking the idea from mathematics and somehow creating something trainable from this. So they say that we have some problems with graph neural network like our smoothing and or squashing. And in this, because of the message passing in graph neural network. But here we use the differential form and integration of differential forms to create something that we don't need message passing, and it is an alternative. We can review the concepts of differential forms like in the paper that we had some explanation also in the homology and cohomology video. So we have like we can associate to the tangent space some forms and some differential forms, and these forms like can be inferred by a neural network, and we use the concept of integration over these differential forms to get our representation by the neural network. So our data is simplexes like embedded, and we define differential forms and etc. and we take the volume or we take the integration to define these kind of neural differential forms. So this is like just ideas in this context. We can see this like in an example. Like this task, we are trying to classify a path. So we have like these three paths, and we have to learn a representation that can distinguish between these paths. We can do it like with one form. So our neural network learns a one form. When we integrate over it, it can deliver the representation. Or we have like use two form or three form and etc. You can see various examples in this paper also. So in the past paper we were using the metric. In this paper we took the idea of the differential forms and made it like trainable. So the title of the video, mathematical structure or trainable. Our last paper is Lie neurons. So we are using the ideas from Lie algebra, and we generalize some kind of neural network like SO3 equivariant, which is called vector neuron, and we construct a network that is equivariant on the Lie algebra, like convolutional neural network are equivariant with respect to distances. So the notion of equivariant was that enables the model to output a change like in a predicted way. When we change the input, the output is changed in the same way. And with the concept of Lie group and Lie algebra, we defined like we have like a Lie group G, and we have a Lie algebra associated to it. we have the concept of like a Lie bracket or etc. And we have to define some bases for these Lie algebra also and behave like a vector space. So they define some operations like they call it V and the hat to take elements from the Lie algebra and represent it in the vector space like Rn, and a hat also that represent the idea. So in the appendix you can see how these V and hat behave as an example. So like for example, we take like SO3, which its elements are skew-symmetric matrices, and we have these bases. So we can define this element using these bases, and we have that concept of V and hat used here. The concept of adjoint representation is defined also using a map from the Lie algebra to Lie algebra, but we take some elements from the Lie group, like we have AX, A minus 1, so we apply this product. And we have the concept of killing form also. These are standard concepts in a Lie algebra, which is defined using a bilinear map. It takes two elements and outputs two elements, so the killing form is also invariant under the adjoint action. Using these concepts, we create some layers and we train a Lie neuron or a Lie neural networks, which have different, like we can define different activation function and etc. Again, here we are taking concepts from the Lie algebra and we are adding something trainable in the process. So they try to generalize an SO3 equivariant neural network to different spaces like symplectic space, which are used in like Hamiltonian mechanics in physics and etc. And they are using it for different tests. And you can see the result also. They are getting a good result compared to other methods. So we have gone through a lot of concepts from Shaef and etc. and we made some trainable, and we see a lot of examples that we are taking some ideas from mathematics and we add some trainable features to that are really solving some very specific tasks. I hope you liked the video. Don't forget to like and drop a comment if you have a question, and also subscribe.